Okay, so in this video, we are going to see how to implement RAG using LangChain framework and Fire's vector store, and for LLM, we'll use OpenAI. Okay, so let's get started. In this first cell, I have declared a variable OpenAI API key, which contains a valid OpenAI API key, and I'm assuming you know from last week how to get an API key from OpenAI. So moving on, we would need to install a few packages which are not there in Colab by default. In LangChain itself, we would need multiple packages, and another thing to note is that with time they keep changing also, right? So at any point of time, if you are implementing RAG, you should make sure what changes have happened in LangChain, um, uh, functions and classes, so that you get to use the updated packages, and whatever changes have happened at any point of time, you should check them out in the documentation. So I am using LangChain, LangChain core, LangChain community, and LangChain OpenAI. These packages we would need for this demonstration. I would also like to show you the versions which I'm using at this point of time, so that you can verify. These are the versions of LangChain, LangChain core, and LangChain community that I'm using. You can also run pip show to see the versions. So you can use either of these codes to see which version you are using. You can either use this attribute __ version __, or you can simply use pip show. So these are the versions that I'm using. Okay. So the first thing is to obtain the LLM, right? There are multiple steps in RAG implementation. We would need an LLM, and then we would need to create a vector database, and then we would need a retriever, then we would need to create a pipeline to combine all these components. So the first thing that we are doing right now is creating an LLM, accessing an LLM basically. So this is a wrapper you might have seen in the previous week. From LangChain _OpenAI, import chat OpenAI. This is an LLM wrapper in LangChain. We are going to set this environment variable. So in the very first cell, I had this variable OpenAI API key, which contains a valid API key. I'm passing that on to this environment variable, right, using this package OS. If you don't want to do it, there are also other ways. I will keep showing you. So we'll use this wrapper chat OpenAI, where we'll pass whichever model we want to use. In this demonstration, I'm using GPT 3.5 Turbo. You can use any other model of OpenAI also. Then the next parameter that I'm passing is temperature. I'm passing it to be 0.7. You might know that this temperature controls the creativity of the LLM. It is optional. You can skip passing it. And if you have not created this environment variable, you can pass the API key over here also. Okay. Now we can test this LLM out. Okay. Using this invoke function, LLM.invoke, I am going to pass in the query that I have, and we'll see the response. Now, on a high level, what we're going to do is in this demonstration is the following. I will ask this LLM about a hypothetical company. This is just a hypothetical company. So I will ask something about this company to this LLM, and it will not be able to answer, of course, because it has not seen that information, right, about this company. So it has generated some response. Of course, it's not exactly what we are looking for, right? So that is what we want to do in this RAG demonstration. We would pass in some external data in the form of either a text file or a PDF file or any other form. So these two files I've already uploaded to Colab. Let me show you the content of these two files. This is the text file. Some basic information, just a small piece of information. It's a small demo. One paragraph of information about this company I have added here: when it was founded, where it was founded, and what it designs, etc. That's all. So this is the information we want the LLM to access during RAG. You can ask any other question also to LLM regarding this company based on whatever you see in this text file, and it will not be able to generate the right response because it doesn't know about it. Makes sense, right? Okay, so now we want to perform RAG so that the LLM is able to correctly answer about this company. There are several steps, as you know. The first step is to read the data for retrieval. In our case, we have this text file as well as this PDF file. By the way, this PDF file also contains the same information exactly as the text file contains. I'm including it just to show you different kinds of files that you can load into RAG. So we'll prepare the data for retrieval, then we'll split the text, right, into chunks, and then we'll generate embeddings for all those chunks, and finally we'll store these embeddings into the vector database, and then we will create a retriever which will be able to retrieve these embeddings from the vector database. Finally, we want to combine this LLM and the retriever. So these are the 6 steps that we are going to perform. Let's go on. The first step, read the data for retrieval. There are several kinds of files which can be loaded to RAG, but I am going to show you these 3 ways. One is the simple text, that is not a very real world situation. I mean, you pass the text there and then in as a document object. I will show you that. Second is the text file that I have uploaded here already. Third is the PDF file that also I have uploaded here. So these 3 kinds of loading data I am going to demonstrate. The first one, using a simple text. One thing to note, each kind of data, external data that you want to load to RAG is finally stored in the form of what is called a document class, right? So LangChain wraps all content in what we call document objects. These objects will contain, of course, the text that we are uploading, as well as some metadata, some extra information about the data, which is which file it is coming from, etc. So in order to create a document object, we would need to import from LangChain _ core dot documents import document. Okay. Earlier it was like from LangChain dot documents import document. So earlier this document class was available in LangChain. Right now it's available in LangChain _ core. So this is also I wanted to add that in the beginning I told you, whenever if you want to implement RAG, you should check out the changes that would have happened in the library, because these changes are happening quite quickly. We'll create an object of this document class, and 2 important attributes that we'll pass, 2 important parameters. First is page content, second is metadata. So here we are passing the page content here itself. This is just a small demo, so I'm just showing you how to pass this small text, but you can pass any meaningful data quickly over here. You can pass a long paragraph or one document information directly over here. You can pass. The idea is to convert every piece of text in the form of a document object. That's all. Here you can pass the metadata, any piece of information you can pass about this data. So let's see what is there in this doc object. So this data has been converted, this This data has been converted into a document object with these two attributes, metadata and page content. You can access these attributes individually also like this. We would be needing these two attributes, at least page content attribute, towards the end. Okay, if you want to upload a text file to RAG, then you're going to use something called document loaders. There are different kinds of document loaders. For example, if you want to upload a text file, there will be a text loader. If you want to upload a PDF file, there will be another loader. If you want to upload an HTML file, there will be another loader. If you want to pass in some information coming from a URL, there will be another loader. So depending on what your scenario is, what kind of data you want to, what kind of file you want to upload, you'll look for the appropriate loader and bring it in. So from LangChain underscore community, now it is present in LangChain underscore community dot document underscore loaders. This text loader will import and we'll create an object of text loader, wherein we'll pass the name of the file which we have already uploaded here, and then we'll call loader.load. So this docs1 object, docs1, let's see what is there in docs1. So this docs1, please note, will be a list of document objects. Now you might think that we are passing only one text file here, then why is it a list of document objects? So this is the default behavior. Even though you pass one file, you can pass multiple files over here as well. You can pass multiple files, multiple text files over here, and they all will become, after loading, they will become something that is a list of document objects. Okay. In this case, there is only one text file. Nevertheless, the list will contain, it will be a list which will contain one document object. We can iterate over that. For doc in docs1, we are just printing the page content and metadata. We are just accessing these two attributes, and this is what we are getting. So now what we have done, we have converted our text file into a document object. Similarly, if you want to load a PDF file, you will have to install PyPDF. Okay. Run it. Okay, after that, the document loader that you would need is PyPDF loader. Okay, well, there might be probably a couple of other loaders also for loading PDF file. You can experiment with them. In this demo, I'm using PyPDF loader. The rest remains the same. You'll just create an object of PyPDF loader. You'll pass the file which we have already uploaded over here. We'll create this loader and then loader.load. This will load this PDF file over here as again it will create a list of document objects. You can iterate over this list of document objects. Again, in this case, we are passing only one file, but it will be a list of document objects. We are just printing its attributes. So if you want to upload a CSV file, you will use CSV loader. If you want to upload an HTML file, you will use unstructured HTML loader. If you want to use a PDF which is available online, you will use online PDF loader. So just look up, depending on how your files are, what type your files are, just look up the appropriate loader and load your files. So far, I have shown you loading one file separately, one text file separately, then one PDF file separately. But in general, your data may lie in multiple files. Some of these could be PDF, some of these could be text, and so on. So you can load all of them, assuming your data is present in 4 files. First file is a text file, second is a PDF file, third is a CSV file, fourth is an HTML file. So you can use these different loaders, and then what you can do is you can concatenate them. So this is very easy to use. As you can see, you can just concatenate them. So this will contain all the documents, right? So all the documents will be contained in one particular variable, which will be a list of document objects with which you can proceed. Okay, so in one example itself, I'm using multiple loaders, and this plus, plus is being applied to two lists, which will just concatenate their contents. So this all docs will finally contain a list of all the document objects. Okay, that was first step, loading the data into document objects. Second step is splitting the text into chunks. As we know, we can't pass on these huge files. They could be huge, right? So we can't pass them on just like this. We need to split into smaller pieces. For that, again, there are several splitters. In this demo, what we're going to use is recursive character text splitter. This is what we are going to use from LangChain _text_splitters. We will create an object of this recursive character text splitter, and we will pass some parameters. Two of these are important. First one, of course, is the chunk size. This is in characters. This is a small file, as you know, so I'm keeping it to be very small values, but in general, in a practical scenario, you might keep some around 1000 to be your chunk size. The next thing is chunk overlap. In this case, I'm keeping it 15. In general, you might want to keep it to be 10 to 20% of your chunk size. Okay. And then using this splitter object, splitter.split documents, you're going to split your documents. Let's see what this chunks contains. So you can see that your documents have been split. Okay. This is a list. Again, this is a list of document objects where your different chunks are available in one document. This is your first chunk. This is your second chunk, and so on, depending on how long your the content of your file was. Some number of chunks will be created. Okay, you can. So here I'm just printing the page content. You know, there are two attributes of every document object. One is metadata and second is page content. So I'm just showing you the page content over here. So this is how our file's content got split. This is the first chunk. This is the second chunk, and so on. Right? The other thing to note is this overlap. There's in Helsinki here and Helsinki here. So this is the overlap, right? So now our data has been, our text has been broken into pieces. You can just check out the lengths of different chunks, right? This is the chunk size and overlap that we had mentioned, and then that created 11 chunks for us. The length of first chunk is 42 characters. The length of second character is 39 characters, and so on. You might be thinking we mentioned the chunk size to be 50, then how is it all not 50? The reason is that this recursive character text splitter does not split the moment 50 characters are over. It doesn't blindly split. It splits at meaningful boundaries. For example, wherever there is the sentence wherever the sentence is ending, or wherever the word is ending, wherever there is some punctuation mark, that is where it will try to split the content. For example, here, you know, the words are finishing. It's not that between Helsinki somewhere the split is happening. That is not how it works, which makes sense also. So that way this character text splitter is meaningful to use, right? So depending on where the word is getting over, this will be less than 50. Okay. All right. This is actually just the same thing. we can just test out. I'm passing a very small value here. Just an extra example. Can ignore this actually. What I want to show here is the following. Let's say this is our text, okay, and there and then if you want to see how this text will be split, you can use this additional function which is split underscore text, and I'm passing very small value so that you can really understand what is happening. Even though you're using recursive character text splitter, but if you pass very small values, for example, chunk size is three characters only, it is bound to break at you know, within word. The words will be split. Inevitably that will happen because you have passed chunk size to be very small, and it is not a you know, meaningful case where you pass in very small chunk size, because the information will be lost in splitting. So you should mindfully pass the chunk size as well as chunk overlap. This is just for demonstration and for playing around. So now we have split our text into chunks, and the next step is to produce embeddings for each of these chunks. For that, we are going to use OpenAI embeddings. There are several kinds of embeddings that we can use. You can explore that. Since we were using OpenAI LLM here, I'm using OpenAI embeddings. From LangChain underscore OpenAI, I'm creating an object of that. Now, in order to embed the documents, which means create an embedding for all these chunks, we're going to use this function embed underscore documents, wherein we are going to pass a list containing the text. Note, we don't need to pass any extra information. We just pass page content, which contains the actual text of each chunk. So doc dot page content for doc in chunks. So these chunks we had earlier created while splitting. These chunks we had created earlier, right? We are going to use this. This chunks was a list of document objects, and we are passing the page content for each document to this function embed documents. To retrieve the vectors means the embeddings, the length of each of these vectors, this is how many vectors got produced. There were 11 chunks, so 11 vectors will get produced. If you want to see the length of each vector, that is this much. This is predefined. You can change it also. Some parameter. I am using default value. So this is the length of the vectors that we are getting. That was third step. We have now created the embeddings. The next step is to store these embeddings in a vector database. For that, again, we can use several options. We can use Fires, we can use Pinecone, Deviate, Chroma. In this demonstration, I'm using Fires, which is by Facebook AI Similarity Search. Okay. It's one of the popular vector databases. You will have to install it using Fires CPU package, and then once that is done, from LangChain underscore community dot vector stores, we are going to import this Fires. Now, in order to store the embeddings into this vector store, what we are going to do is we are going to pass two parameters. The first will be the chunks. Chunks, you remember, was a list of document objects, and second thing is the embedding model, which is OpenAI embedding model that we were using. Whatever I showed you earlier, this is just a demonstration how to create embeddings, but here when you pass it to a vector database, it will automatically create the embeddings. So you just have to write fires.from documents, where you just pass in two things. One is the documents, and second is the embedding model that you want to use, and that will be, this embedding model will be applied on these chunks, and the vectors that will be generated will be stored in this vector database. Just this statement is needed to do two things. One is apply an embedding model to the documents, to the list of document objects, and the embeddings that will be produced out of that will be stored in this vector database, which is this variable for us. So this is a vector stores.files kind of object. This is a vector store for us. You can access some properties of this vector store. You can see that these chunks have been stored in this vector database. We are accessing the data associated with each chunk. This is the data associated with the first chunk, and so on. Okay, the vector database has been created. Now, we have done so much hard work in creating this vector database. The moment I close this code, right, the vector database, we will have to create again next time when we want to use it. So the better idea is to store this vector database in some persistent storage by using this function save_local, so that locally we will store a copy of this vector database, so that next time when we want to implement RAG using the same text, of course, we would simply load it. Okay, so these two functions you can make use of to save vector database and to load the vector database from a local storage into your code. You will have to mention, of course, the embeddings that vector store is using. So you can continue with this object new store in the subsequent code. Another thing that I want to show you is you can run a similarity search on this vector space now. For example, you can pass in a query and you can pass in how many relevant documents you want which are closest to this query from the vector store. So similarity search is a function that we are using, and what was the launch date is our query, and based on this it has given us two chunks, two relevant documents from the vector store. Okay, this is a page content. This jet sneakers, this is coming in the first chunk, and then because we are asking for a date, there's a year that is given, not the date, but the year is given. So that is another point to note. We are asking for a date. Imagine we were doing keyword search. Now there is no date in the document. So in fact, for keyword search, you would have to exactly see a word which is date, which is very unlikely, right? So that's not meaningful. That is why these embeddings are useful. Embeddings will give us a closest vector. It may not be exact. It may not be using the exact keywords, but it will be closest in the space of embeddings. How is the similarity measured? Several metrics can be used. For example, cosine similarity or L2 distance can be used. There is another function, similarity search with score, which will return the exact score, which means what was the similarity. So this was the first the text contained in the first chunk that we retrieved. This is the score. This is the second chunk, and this is the score. So in general, we fetch some more than one chunks, because one chunk may not contain all the information. So this value of k can be varied. Here I am just demonstrating with 2. You can pass in some 4, 5 or something. Okay, next step. So we have created the vector database now. The next thing is to create a retriever. From this vector database that we have created, there is a function .asRetriever. So we want a retriever from the vector database, which we can use along with the LLM. Okay. This is where you can pass in the value of k using this attribute. You can pass in the whatever value of k you want, which means how many chunks you want to retrieve. You can test this out now. Using this retriever, you can test this out, that if you pass in this query, what it is doing right now is this retriever is retrieving some relevant documents. We had passed k is equal to 3, so it is retrieving 3 documents. This is just a testing. We have not connected it with LLM. This is just testing that the retriever is working fine. Finally, the last step of RAG is to combine all these pieces, which is combine the LLM and the retriever, these two pieces mainly. Of course, the prompt finally That's the third thing, the prompt that the user will ask. So these three things we would need to finally see whether the RAG is working fine or not. For that purpose, the first thing that we would need is a wrapper for the prompt. This you might have done in week 6. Chat prompt template from LangChain_code.prompts. Second thing that we would need is str output parser. The output would be objects of document types. So a message type in this case. After we get the output from LLM, that would be an object of message type. You want to convert into a string. So for that, you would need str output parser. There are some other parsers also. You can use any one of them. Finally, runnable pass-through. It will tell that the query has to be passed as it is. So let me show you its usage. Okay, let's go step by step. First thing, we will need a template to create the prompt, right? This is the template that we'll use. Use the following context to answer the question. Use 3 sentences maximum and keep the answer concise. So whatever high-level piece of instructions that you want to pass, you can pass here. Then context, this is a placeholder that we are creating, and then question is a placeholder. Question will contain the user's query, and this context will contain whatever information we are getting, we are retrieving from the vector database. So now we need to tell what the context is going to be and what the question is going to be. Then we need to create an, we need to call this function from template from this chat prompt template, wherein we'll pass this template, right? The next thing is we need to create a pipeline, the RAG pipeline, the final thing that we had to create. In that pipeline, there are going to be 3 main things, these 3 main things. We need to pass in the prompt. How would this prompt be created? This is a template of the prompt that we created. In order to actually create the prompt, we need 2 things, which is the context and the question. Now, where would this context come from? You know that we are doing RAGs. This context will come from of course, the question is there. Question is there that the user will ask, but the context information will come from the retrieved documents. For that, we are going to use this retriever, but this retriever might fetch multiple documents from the vector store. So we need to combine all of them to get our overall context. Let's say the vector database gave us 3 documents, 3 chunks. So we need to combine them to create an overall context. So for that purpose, we are creating this function, which is all that it is doing is joining different chunks. So let's say the vector database gave you 3 relevant documents, then it will join the content, page content of these 3 documents separated by 2 line spaces gap, just to tell that that's a different chunk. So that is going to go as a context. This is a small pipeline that we have created here, which means first retriever will retrieve, and whatever retriever retrieves, we are going to call this function to join their page content. That is going to be our context. And the question is the same whatever user asks, right? So that's why we are going to pass a runnable pass-through. That's simply pass-through. That's all. And then using this context and question, we will create our prompt, right? Because this template had these 2 placeholders. That those placeholders we have passed. Second thing, of course, the LLM that has to run. LLM object we had already created in the beginning. That is the object that we are passing here. And finally, this LLM will give us some output that will be in the form of message objects. We are converting it to a string using this str output parser. Now, if I ask a question to this LLM, so my query is again the same: when and where was this hypothetical company founded? I'll pass in this query. And then in order to finally run the RAG, I'm going to use the same function, but I'm not calling it like llm.invoke. Now I'm calling it like ragchain.invoke. This ragchain contains the pipeline of RAG, right? Let me see. Now it is able to tell us correctly, right? So this was a hypothetical company. Of course, the LM wouldn't know anything about this company because it wasn't there in its training data. So we are passing in an extra document which contains some information about this company. And now you see after this, after running this RAG pipeline, this LLM is able to give us the correct answer. So the moment you ask a query, it will first check for the required information in the vector database. If it finds, then it uses that. It gives priority to that. So that's how it works. So this was an end-to-end demo using a very small, of course, an example data to carry out RAG. Now you can use these steps to carry out this RAG pipeline in a real world scenario, use some real world data. And the moment your data changes, all that you have to do is you have to update your vector database. Just that one step you have to change that we did, I think step number 3. You just have to update your vector database. Everything else remains the same. So that's the beauty of it. There's not a lot of change that your code will undergo if the information comes in afresh. So that was about a demonstration of RAG. I hope it was useful. Thanks.